what can we do in EDA to actually make better quantum computers? In the end, yeah, I mean, in EDA, we are about design automation. We are about making better designs. And then thirdly, really talk about what could quantum computer potentially mean for EDA? Right? Is there, when and how could we potentially take advantage of quantum computers? So let me start with the first part. What is the current state of quantum computers? So what you see on the right here is IBM Q System 1. And this is a fully enclosed quantum computer. It doesn't need to be in a lab. It can actually be placed in any data center. We have one in Poughkeepsie that is just standing next to a big IBM mainframe. You look at sort of a big glass enclosure, which is made from borosilicate glass, which actually is very special glass. This is glass that's being used by a company, being manufactured by a company in Milano called Copion for us. They are famous for the glass they produce to protect the Mona Lisa in the Louvre and the crown jewels in London. And we use it to really protect our very delicate qubits. Because as you will learn throughout this talk, I mean, despite the fact that we have come quite far in quantum computing, qubits are still very finicky and very delicate. Right? So to protect them from noise, ambient noise, vibrations, temperature fluctuations, electromagnetic waves, helps a lot to kind of improve the quality of a quantum computer. And I'll show you throughout the talk kind of how we measure the power and the quality of a quantum computer. And you'll see that by encapsulating and closing them well, it certainly gives a nice boost beyond like the base capability of the quantum computer. So let's look kind of what's inside here. What do we see inside a quantum computer? So first there is the chip. The core chip is the superconducting qubits and resonators. That chip sits on the PCB, which has quite a bit of shielding to protect the chip. So this is all sitting in the bottom here of this cryostat, running at about 15 millikelvins. And then you go up in the stack layer by layer by layer, and each layer things get warmer, right? Getting up to kind of the 40 Kelvin, and then you go into the room temperature, and then you go into the stack on the right, what you call kind of the room temperature electronics. So most of the elements, most of what you see in the stack here is basically wiring. It's wires to basically take signals from the chip and bring them to the control logic. And on the right here is a huge rack of microwave pulse generators that basically are used to program the qubits and also to read out the qubits. So looking a little bit closer, how do you basically interface with the quantum computer? What IBM made available is something called the Qiskit. This is basically a bunch of Python API layers and a lot of functions that can run on classical computer. On the classical computer, you run the interpreter, the compiler, and you basically turn that into a set of assembler-like quantum instructions that are being executed by this rack of FPGAs that create basically microwave pulses. So then these pulses, they go in the input module, go through the cables, the filters, the attenuators, and basically get into the quantum chip. And then on the other side, after the quantum processor does its operations, you kind of read out the signals, they find their way back into this control logic rack and are being translated into classical zeros and ones that are being fed back to the application. So we look a little bit more closer at the chip. IBM implements our qubit chips with Josephson junctions as nonlinear inductors that do the qubit computations. And then we use basically microwave resonators for a couple of purposes. One is to read out the qubit states and also to create the buses between the qubits to basically create the entanglement. And furthermore, we can program them kind of to do some isolation, to propagate or cancel out noise to ensure that some of the qubit operations can operate more reliably. So this is sort of the basic overview of the hardware. So let me go a little bit into kind of some of the basic theory of quantum computation, and then kind of bring it back kind of to show where the state of the art in quantum is nowadays. Yeah, so quantum computers, they work with qubits, and the interesting property of the qubits is that it cannot only be a 0 or only be a 1, but you can think of a qubit as basically being able to take on any value on this globe. Yeah, so basically any superposition of 0 and 1, depicted by these arrow here, where a bit lands on the sphere, is a valid qubit state. And the notation that we use for this is basically a certain amount of 0 plus a certain amount of 1 that gives us a vector and it positions us somewhere here on this globe. So what's immediately clear that this superposition phenomenon of a qubit is extremely powerful, correct? So one bit can represent an enormous amount of state space. And that's one of the fundamentals of a quantum computer, and that with relatively few bits, you can represent enormous amount of state spaces. So what if you have more qubits, right? If we have 1 qubit, we get basically 1 complex state. If we have 2 qubits, we basically can take on 4 combinations of these complex states. If we go 3 qubits, we can do 8, correct? So this is the first qubit, the second qubit, first being a 0, second being a 0, here the first being a 1, the second being a 0, and so on and so forth. So we basically get 2 to the n complex terms if we have n qubits in our machines. So the number of states that a quantum computer can represent is phenomenal. And that's where a lot of the power of a quantum computer comes from. Unfortunately, when we measure the state of a qubit, it collapses back to 0 or to a 1. So many computations that we carry out on the quantum computer, we do probabilistically. So you run an experiment n times, and then you look how many times do we get an answer 0 for a particular bit, how many times do we get a 1 for a particular bit. Again, the notation for that is that a square is the probability we get a 0, b square a probability to get a 1. So for example, this state, which is basically a state on the equator here, has an equal probability of collapsing to a 0 or to a 1. And this state vector is basically tilting upwards in the negative direction, and has therefore it has therefore a higher probability of becoming 0 versus a 1. So this is what we call a measurement of a qubit. So the measurement really takes a complex qubit and maps it back to 0 or 1. So that's the kind of quick description of the meaning of a superposition. The other really interesting phenomenon of a quantum computer is sort of the ability of 2 qubits to entangle. And the simplest description is that 2 entangled qubits cannot be described independently of each other. But it's a very, very powerful phenomenon, correct? So if we know that this qubit is on this state, this state here, we for sure know that the corresponding qubit is exactly in this state. And it doesn't necessarily have to be the identical state. It could be this one, could be connecting to some other states and be entangled with some other state of the globe there. But the really very interesting phenomenon is the fact that if you know one, you know for sure what is the other. So how do we notate this? Again, here is basically the state space that describes 2 qubits. A, B, C, D. Being complex numbers. that describe basically the state where the first bit is a 0, second bit is a 0, or the probability is, the first is a 0, the second one a 1, and so on and so forth. So in the case that 2 or more of them are non-zero, and we cannot separate out the qubits, then they are entangled in a perfect correlation. And so for example, this state is not entangled, and each of these two states are entangled. And let me just simply show you kind of why. Because this state we can rewrite basically by pulling the 0 state out of here, and have this part of the equation left. But this state, we cannot write as a combination of two single qubit states here. So these are fully entangled, which means if we for sure figure out that the first one is a 0, we know that the second one is a 0. Or the first one is a 1, we know for sure that the second one is a 1 here. So once you measure one qubit, you know for sure what the other qubit is. So this was a very, very quick view of sort of the basics of quantum computing. So let me switch a little bit. How do we now practically use a quantum computer? So to program it, you can, as I mentioned before, either use like Qiskit and a Python layer, but we also have made available a quantum assembler editor, which is probably the best way kind of to graphically describe how programming of a quantum computer works. And let me give you just a simple example here that gives you a pretty good idea. So what you see here is 5 lines. Each of these lines represent qubits. Qubit 0 to qubit 4 here. Each of these boxes on here are basically operations that you perform on a qubit. Some are single bit operations that only work on a single bit. Here, for example, we see a C0 operation that works on 2 qubits. So a single bit operation, for example, is this Hadamard gate. What it does, it takes a qubit out of its 0 state, which is pointing upwards, which is the rest state, and puts it on the equator, where it has kind of an equal probability of being a 0 and a 1. To represent the fact that 2 qubits can be entangled, we have a C0 gate, a conditional NOT gate, and depending on the value of the controlling signal here, it will either flip or not flip the state of the other qubit. So it will basically flip it completely around in the state space over the globe here. And then we have a bunch of other single bit operations like the X, the Y, and the Z, and pretty much they are all flipping around the particular axis of the block sphere. And then finally here we have this little gate which represents the measurement, which takes a qubit's complex value and maps it back to 1 or 0. And what you do with these programs, as I said, you can either run them on real hardware. IBM put out a couple of years ago the first quantum computers that you could access through the cloud, or you can run them on simulators. And what you normally do, you run them a significant number of times, and you get a probabilistic answer. You see how many times you get a 1, how many times you get a 0, and if you run enough times, it usually kind of converges fairly rapidly. So this gives you a little bit of a feel how to program a quantum computer in the assembler type of layer. So how do we measure the power of a quantum computer? So where are we kind of on this journey in making quantum computing really work? I mean, I think it was one of the earlier talks that I quickly had the opportunity to attend in the conference here, where one of the speakers was talking about sort of an image recognition. He said, hey, the quantum computers are not powerful enough. And it's true. We are at the beginning of this journey, but we are at a pretty steep curve. And I think in a couple of years, we're going to see significant quantum computers and quantum compute being able to be used in production type of applications. So if you look at a classical computer, yeah, you could say that roughly, yeah, the computer power of a computer double every time we kind of can double the number of transistors, right? So more or less the traditional type of Moore's law. If you look at a quantum computer, yeah, the potential, and again, important word here, the potential power of a quantum computer doubles every time you add only one quantum bit. This is pretty powerful, correct? So that, yeah, goes up very, very rapidly. Unfortunately, yeah, the word potential, as I mentioned, is very important, because this is only true if you have perfect quantum bits. And right now, we are still pretty far away from having perfect quantum bits. But hey, we know what to do, correct? If we don't have really good bits, like in SRAMs, we do error correction. So we can do the same thing in a quantum computer. So indeed, you could build a universal fault-tolerant quantum computer, where every logical qubit gets mapped to significantly large number of physical qubits, yeah, to guarantee that the qubit will function, yeah, 100% error-free. Unfortunately, the estimations, yeah, currently are that you probably need 1 to 5 million physical qubits, yeah, for, yeah, as the overhead to produce really extremely high quality, perfect logic qubits. So clearly, this is still very far from practical. However, a couple of years, yeah, John Preskill observed that, hey, you know, there's probably a lot of interesting stuff we can actually do with quantum computers that are, yeah, that don't have full tolerance yet. And he introduced the term of approximate quantum computer, near-term intermediate scale quantum computers. And with that, yeah, the estimates are that with, yeah, large, yeah, a few hundreds to several thousand bits, we can actually start to do pretty interesting quantum type of computations. So let's take a look at it a little bit more. So how do we measure, yeah, the power of a quantum computer? So one of the things that IBM proposed about at the beginning of last year is the metric of quantum volume. Yeah? And quantum volume not only takes into account kind of the number of qubits that you have, but really looks on, yeah, the connectivity among qubits. What functions can you do? Can you only do very simple functions, or can you actually execute significantly more complicated functions? What are the error and decoherence times of the gates? Because as I said, many of the qubits, yeah, they can only operate for, yeah, a very short period of time. We'll show you some statistics in a couple of charts here. And how many parallel operations can you do? So interesting enough, yeah, if you look at sort of this quantum volume calculation, yeah, both the number of qubits and the error rate are extremely important. Because as long as your error rate is pretty high, so for example here 0.01, even if you add, yeah, if you double the number of qubits, going from 100 to 200, you don't get any increase in quantum volume. Yeah, while on the other side, if you have a reasonable number of qubits, yeah, and you are able to cut the error rate by a factor of 10, you might actually get an increase in the quantum volume, yeah, the measure of the compute power of the quantum computer, by a factor of 24. Yeah? So what really counts is not only how many qubits you have, but the quality of each of the qubits, how they're interconnected, and how powerful are, what powerful operations can they really execute. So let's look at a couple of these metrics. Yeah, so IBM publishes most of the metrics on our website for each of the machines that we have on the cloud here. So if you look at the glass enclosed machine that I showed, that's the last column here, I'll give you a feeling for some of the error rates. Yeah, so single bit errors, basically one single bit doing wrong operations, are here in the 10 to the minus third, yeah, 0.1 to 10 to the minus third type of range. if you look at the 2 qubit errors, basically an operation between 2 qubits, the errors are in the 10 to the minus 2 rate here. And then we have 2 very important times where, probably the T2, the dephasing time, is the most important. So this is the time where basically a qubit can do its operation, and after that it flips back pretty much to its to a 0 or to a 1. Basically it loses its phase. And that's about 100 microseconds here. So that means with the current quantum computers, you have about 100 microseconds to do your computation, and you still have a certain amount of errors that take place while you are doing these computations. So how do we measure quantum volume on a quantum computer? The way to do that is basically run a benchmark circuit. So this is a set of benchmark circuits that IBM developed to calculate quantum volume. Think about it kind of as a spec mark type of benchmarks, which are very, very dense circuits. So first you kind of do random permutations of a bunch of qubits, then you have a whole bunch of 2 qubit operations, and you keep on repeating that d times, and you basically figure out how much of this can I cram into my quantum computer and still get a reliable answer. So this is sort of the depth of the circuits, how many times can you keep on computing, and this is the amount of compute that you can take place in each of the cycles. And depending on how much time you have, your 100 microseconds, you can basically do more layers of this type of computation. And this has become a pretty good benchmark to compute how powerful a quantum computer really is. So if we look at that and start to plot that, the first machines that IBM put out on the web were the machines of the Tenerife generation. This was a 5 qubit machine and had a quantum volume of 4. The first generations of 20-bit machines were the Tokyo generation, had a quantum volume of 8. Then the next generation, the glass enclosed, also 20-bit machine, had a quantum volume of 16. So you see that every year, we have been able to double quantum volume. And if you look at it, this curve should be very familiar, correct? This is pretty close to Moore's law, where compute power or compute density was doubling pretty much every 2 years. So what we believe, at IBM, that we are really at a pretty steep starting point, and we'll see major improvements in quantum computer capacity in the pretty near term in the next couple of years. And this was a chart that I showed last year. And if you look at the announcements earlier in the year here, we have added our Rolly machine. This is a 28-bit machine that has a quantum volume of 32. So again, one more data point here for the 2020 generation. So we believe that there are enormous kind of engineering challenges to climb up this curve, but there are no fundamental limitations to significantly climb up this curve in the next couple of years and significantly increase the quantum volume. So where will this get us? Once we start to get to the realm of having a couple of hundred to a couple of thousand bits, you can start to do some real interesting quantum chemistry. Early algorithms already look very interesting, very promising, and even with lower number of quantum volume. So we expect that in the next 5 years, in optimization, quantum chemistry, heuristic machine learning, significant developments will take place, both on the algorithmic side and supported by the faster higher quantum volume computers that people will be putting out there, it will start to become very realistic to run real set of optimization problems on these types of machines. Yeah, so therefore it's really the time for people to start to think, okay, what would it take to take an algorithm that I have, and what will it take to run it on a quantum computer, and what do I need to do kind of to take advantage of this? So let me switch gears a little bit now. So the next question I said I was going to, now that we kind of gave you a little bit of the state of current quantum computing, the next question I was going to answer was, okay, what can we do from an EDA perspective to improve a quantum computer? And the key to that is really, what can we do to increase quantum volume? And because as I tried to explain, this quantum volume is really a key measurement of the power of a quantum computer. So if you break down the key elements of quantum volume, yeah, first there's of course the number of qubits, yeah, but secondly there's very much the coupling map, right? This like which qubits can actually entangle with each other. Because as you see here from this picture, many current quantum computers are pretty sparse. Yeah, so it means that not every qubit can actually entangle with each other. Only neighbors can actually entangle with each other, yeah, which significantly reduces the ideal power of a quantum computer. So I talked about the coherence time, right? How long can these operations take place? What's the fidelity of each of the gates? The individual errors, and what is some of the crosstalk between each of these bits? So all of these five are really affected by how well a chip can we design, which is really the traditional bread and butter area of EDA, where we can help generate and design better chips. The other part is really is how do we test, calibrate, program these chips. As I mentioned, yeah, there's a lot of calibration taking place early on, where we send a bunch of test circuits and calibrate the quantum computer by adjusting all the different type of pulses. And with that, we can significantly increase the measurement fidelity, the initialization fidelity, and kind of the calibration errors that take place. This is kind of pretty close to what people in EDA testing have been doing for a long time, right? Trying to test circuits, adjust whatever parameters, and create a big feedback loop depending on the actual in-circuit measurements that are taking place there. So a lot of the EDA test discipline can help out here. And then there is sort of the compiler, place, and route part, which takes place is how are we going to take our logic qubits and map them actually to these physical qubits. And depending on how you do this, you get very different answers. You can certainly compact your computation quite a bit if you do this right. If you place the right computations next to each other, you have much less spectator errors from kind of neighbor switching, and you can try to maximize kind of the gate parallelism between each of the operations. And I'll walk you through an algorithm in the next couple of charts kind of to show how each of these improve. So let's look first a little bit what can we do to improve the chip. What can we do in optimization from an EDA perspective, and then talk a tiny bit kind of how we can work on the test and optimization loop here. So the chip, how do you make a better chip? I mean, right now the number of qubits are relatively small. People are working on 30, 60, up to 100 qubits type of chips. So up to now it has been done pretty much by manual layout. But we are getting to a stage where people need some more automated, dedicated place and route that really understands better how qubits interact, how eliminate noise or minimize noise and coupling between each of these qubits. So fast simulation of all the coupling between these qubits, coupled with layout optimization loop that can really place and route significantly larger qubits, is certainly a key area where EDA can help out to start to scale up to larger number of qubits type of systems. The good thing is I think that most of this technology is available. It is very, however, we need to start to put some more effort to really tune it to the qubit type of problem instead of the kind of standard CMOS gates. But if you do it well, you can make significantly better quantum bits. Right here, we show a couple of generations of our machines and how we were able to basically significantly improve the error distribution in the C0 operation. And these are all, I believe, all the 20-bit IBM 20-bit machines. These are the different generations. And by really tuning a lot of the system, we are able to significantly reduce the gate errors that take place there and get much, and therefore improve kind of the quantum volume of the machines here. So talk a little bit about the mapping and optimization problem. Clearly, depending on the topology here, your compiler needs to really follow a different strategy to do a good job in mapping a particular algorithm that's written in logical qubits to the physical qubits that are available on a particular machine. Certainly, very analogous to kind of traditional FPGA synthesis, place, and route type of problems. So let me give you a little bit of a flavor by kind of walking through one of these algorithms here. So for example, let's look at this simple logic program that we have here. We have 1, 2, 3, 4, 5 C0 operations operating on 6 logical qubits here. And we want to map this subsection of one of the 16-bit compute machines here. And one of the things that I did not mention is that actually there is direction, correct, between the qubits. So the coupling direction, it means that we can entangle Q0 with Q1, and therefore the C0 operation can only go one way. So in our current architectures, it's not bidirectional. So let's look at a kind of a simple mapping algorithm that we can do here. So we're going to map the first operation here, gate 0, logic gate 0, which is a C0 between Q2 and Q3. We pick 2 physical qubits. They are connected in the right way, so we can basically map this operation onto this Q2 to Q3 physical operation. And we take the next qubit. We want to do this operation between Q1 and Q0. If we map that to Q0 and Q1, unfortunately, they are connected the wrong way. However, there's a solution for that. We can pick this, and we can actually apply a whole series of Hadamard gates, kind of to flip the bits around, apply the C0, and flip the gates back. Unfortunately, here we are kind of wasting 5 operations, 4 plus 1 in the middle, 5, for one operation. And we're also wasting like 3 time slots for one operation. Right? So we're losing time. As I mentioned, we only had 100 microseconds to do our computation. But this is a little bit wasteful. If we continue like this, okay, now let's pick this operation. So we need to Q1 entangle with Q4. Unfortunately, these are quite far apart, so we need basically this whole path in between here. To get there, we need to swap Q1 and Q2. Then we need to swap Q2 and Q3 to kind of get this logic bit out of Q1 all the way moved here to Q3. And then we can use Q3 and Q14 to do the actual entanglement, the C0 operation, and we can place this here. Then we need to place the last 2 operations here. Same thing here, Q5 to Q3. Need to find a path here, do a couple of swaps, place it here. And finally, we need to execute the last gate here between Q2 and Q3. Need to swap a few times back till we get Q3 close to Q2. And then we can do the final operation here, and our computation is done. So doing this, you can count took us 15 operations, and it takes 12 time slots to do this computation. However, if you want to do this more optimally, you can actually do it in 11 operations and take 7 time slots by placing this thing better. So this is a very interesting place and routing problem, and certainly in reality this is even more complicated because, as I mentioned, certain qubits are more reliable than others. Certain qubits or qubit pairs have longer times that they can compute than others, so you want to use them for the later part of your computation. And then, of course, the whole problem is how do you have the connectivity so that you map this as compact as possible. So the great thing is that IBM has opened this up to the whole community to participate to build better compilers. If you look at the Qiskit software stack, at the bottom is what we call the Terra layer. So the Terra layer connects directly to the actual hardware or connects to special purpose simulators, quantum simulators. And the compilers, like the one simple compiler that I just illustrated, reside in here. So if you want to write a better optimization algorithm that does better placement and routing of these logic to physical gate mapping, you can actually go into the Terra layer and replace the standard compiler that comes with this with a better compiler, which either works better in general or works better for a particular piece of hardware or a particular machine. And IBM actually has regular competitions, where we invite people to kind of submit their best compilers for particular spaces or particular problems. Other key layers in the Qiskit are what we call the Aqua layer, which is a whole bunch of higher level libraries that people use to basically execute financial optimization, machine learning type of algorithms, and I'll talk about that in a few charts. And then there is the Ignis layer, which allows you to kind of to characterize and mitigate some of the errors. And we have opened up what we call kind of the pulse library in the Ignis layer, where you can program the pulses that the FPGA stack sends to the actual quantum hardware and do key measurements kind of to come up with better characterization and mitigation and error type of algorithms. So if you go to this Ignis framework, and there's a key paper that kind of describes how this open pulse system works. You can learn how to basically build your own circuits, execute them, measure some of the key parameters, and use that to put all type of mitigation strategies in place to actually fine-tune how a quantum computer does your particular type of computations. So the Qiskit layer has become very, very popular, and we opened this up in the middle of 2016, and saw a pretty big takeoff in many, many countries. In pretty much a year, it's spread out pretty much across all the different continents. A lot of experiments were being run on quantum simulators, but also a huge number of experiments were actually run on IBM's hardware. I mean, I'm from the Netherlands, so I was very proud to see the Netherlands for a short while be in the top 3 here. And certainly in the first year till the middle of last year, still being in the top part here. Until last April, we had run about 5 million type of experiments altogether here, 5 or actually 10 million altogether here. So if we look now, oops, let me go try to page it down here. Good. If you look at this point in time, late last year, we are about at 29 million of experiments that have been run on the IBM Q Experiment. That's the platform that you can go to on the IBM cloud. About 200 papers have been written by third parties using IBM Q tools and IBM Q hardware. And the Qiskit toolkit has become very popular in the number of downloads and the number of users that we have had everywhere. So if you look at this, we have stretched quite a bit across many different industries. Yeah? And across many different domains here. If you look at this, we have had the chemical industry quite interested, especially in chemical and type of simulations, but also financial industries, healthcare, manufacturing, looking at scenario simulations, looking at optimization algorithms, and even how to apply AI and deep and machine learning on the quantum computer. So what area is really missing here? It's really EDA, right? EDA, electronic design. So I think the question is, how can we as an EDA community also start to take advantage of a quantum computer? And is the time right to get really engaged? And I think the answer is yes. Why? Because it will take a while to really understand how you need to kind of start to think differently and write different types of algorithms that take full advantage of the quantum way of thinking. And let me give you kind of a flavor of a couple of algorithms that run well on the quantum computer that are very analogous to the work that we do in EDA. And hopefully that gives you motivation to really start to, maybe start to look at this and start to get engaged a little bit here. So if we look at various problems that are being classified here, is some of the easy problems, some of the very, very hard compute problems, and then there is a whole space where quantum computers can likely do a very good job. Right? Areas in machine learning, modeling of molecular equations, in chemistry, material science, simulating quantum mechanics, factoring, and we're starting to see some key algorithms in there where quantum compute and quantum algorithms have a real benefit. Let me show you a couple of examples. One of them is Monte Carlo analysis. Right? We do this all the time in circuit simulation. We do it in library characterization. And you can see a nice quadratic speedup in using a quantum algorithm for Monte Carlo simulation. And this is a paper from the IBM Zurich team, if you're interested in this, kind of to show how to rewrite a quantum algorithm to a Monte Carlo algorithm and turn it into quantum type of version. Very, very approachable paper. So, but as I mentioned, you have to really start to learn how to think differently. Right? Instead of our traditional optimization algorithms, we try to pretty much narrow the search space very, very quickly. And no matter if you do branch and bounds or many other places, you try to quickly cut off many, many side branches and try to, as quickly as possible, get to a minimum in the hope that this is also close to a real minimum or a real optimum to the problem that we are searching. So a quantum algorithm is kind of very different. Right? The first thing you're trying to do is say, hey, I have my gigantic state space. How can I actually map this to this huge state space that the quantum computer can represent? Right? How can I encode my problem into all these states? So kind of, you can think about it, you're kind of hovering a little bit above your state space. Right? You're hovering, and hopefully by creating the right inferencing between each of the states, you can put yourself somewhere where there is likely, almost certainly, a local minimum pretty close to you. So I think what we're going to see is kind of a set of like a lot of hybrid computing, right? Where a quantum computer is not going to solve the whole problem by itself, but it's going to be a significant accelerator, for particular parts of your algorithm. One of the things that I'm particularly interested about is, hey, can we basically take the best of both worlds, right? Have a quantum computer quickly go through and read out an enormous part of the state space, get us to a good place, and then we can do more traditional algorithm to really hone in and dot all the I's and cross all the T's and get to a very discrete small solution. And I think these things are possible. Up to 2 years ago, people thought that machine learning and quantum computing were two complete different worlds. there's a paper that was published in Nature in the spring of last year, has shown is that you can actually do support vector machines very, very well on the quantum computer. And yeah, machine learning is becoming more and more interest in the EDA space as well, and certainly has a lot of underlying optimization algorithms that are very analogous to what we do a lot of in the EDA space here. So for example, support vector machine, you try to kind of separate basically a certain number of elements along some key features, light blue, dark blue dots here. And unfortunately, you cannot find an easy separator in one dimension. What you do, you basically go to the second dimension, to a higher dimensional order, where you can actually find the separator line between the two here. So this model, this problem maps very well to a quantum computer, where we can kind of spread out the dots and try to recognize the blue dots from the golden dots. Create a quantum feature map that describes this entire state space here, and build a predictor that can really quickly, in a couple of iterations here, in 5 entanglement steps, basically quickly narrow down and identify very accurately what is a blue dot and what is a golden dot here. This paper is, I would say, very, very approachable, very well written, and it gives you a really good idea how to start to have to think to create a quantum algorithm for a pretty well-known, I would say, traditional algorithm. So what you will see is that, you kind of have, like many quantum algorithms, a section where you kind of prepare your quantum computer. You set everything in superposition. Then you try to build your kind of state space that represents your problem, set up a whole quantum feature map. And then here, is the kind of the compute part, really the training stage here, after which for this particular problem you have a kind of a classifier that does the actual classification. The code is available in Qiskit for the support vector machines. And if you're interested, I think it's very insightful, especially once you read the Nature paper, kind of to see how you need to start to think very differently about your algorithms to take advantage of a quantum computer. So where are we today? A lot of foundational work has been done in quantum computing, but we believe, we are at the brink of a space where for a certain number of algorithms, quantum computers are going to demonstrate a key advantage. For problems that are of real commercial interest, enable real new scientific discovery. And therefore today is really the time that people need to start getting engaged and need to learn how to program quantum computers, how to think in quantum type of algorithms. And at the same time, want to engage the EDA community to start to think about, okay, how can we tune our tools to actually help make quantum computers better and even accelerate the improvement of the quantum volume. At IBM, we have been working hard to create a very open community. There's the IBM Q network with partners from academics, from startups, from key industries. We have hubs at a large number of universities. The way that operates, they are kind of a cluster in the country around which many of the other startups and academic partners kind of work with them. And this is a list of middle of last year. This list is quickly growing here. In addition, we basically here you can find a lot of information on the IBM Research IBM Q webpage. There is the Qiskit.org, which is completely available in Git, and the Qiskit.org website, where you can find the latest version of the Qiskit code. There is the IBM Quantum Computer, IBM Q Experience, where you can run simulators, you can run on real hardware, you can run on high-performance computing, IBM Cloud. And then there's the IBM Q network, where you can kind of become part of the inner circle and have access to the latest machines and do collaborative research with the IBM team in addition to all the open areas that we have opened up for the broader community here. Yeah, I think in conclusion, yeah, I think we are at a pretty exciting time here. Yeah, we believe that quantum volume will increase very, very drastically in the next couple of generations, and for the next couple of years. Therefore, we will be able to address more and more interesting problems with quantum computers. And we are inviting a large part of the community to really get engaged and start to learn how to think differently. I mean, I remember, how long it took for people actually to get used to parallel programming and really start to take advantage of multi-threading and multi-cores. And that was, I would say, minor paradigm change from straight sequential programming. Learning how to program a quantum computer is really even a huge mindset change, and therefore it's a good time to get started now and be ready when these machines start to be powerful enough to really start to make a significant difference and create a quantum advantage above conventional computing. With that, Jose, I'll hand it back to you, and I think we have a couple of minutes for Q&A here for the next keynote.
Thank you very much, Leon. It was a very interesting talk. Floor is open for questions. I only ask you please to identify yourself if you raise a question.
Hi, this is Swarup Ghosh from Penn State. First of all, thank you so much, Dr. Stoke, for a very inspiring talk. I want to ask you a question about the quantum volume. You mentioned that the quantum volume is increasing, doubling every technology generation. So could you please comment on what kind of recipes are followed so that the volume is increased?
Yeah, so I think it comes from many different places. One is basically making better chips. So better chips basically mean making chips that have more bits. It have more bits that can be coupled to each other, so have a denser connectivity map, and can do so at lower errors and with less crosstalk. So I think that is a big contributor from the core hardware side. But at the same time, better compilers make a large contribution as well. I think this is a simple example, as I showed. If you can compact your computation, and cut it by 1/3, you can certainly get 1/3 extra amount of power out of your quantum computer, because as I said, after 100 microseconds, your whole computation falls apart. So the more you can do in the fewer number of steps, the better you're off. Then people are working on different hardware approaches. I think if you look around the industry, you see different in addition to the qubits that IBM and various others are supporting in superconducting qubits, you see people looking at ion trap systems, semiconductor spin-based systems. So what you're seeing, I think, is a lot of energy, both on key hardware, on key compilers and infrastructure, and smarter algorithms that, as far as we see right now, is all accelerating, and therefore we feel that we can probably maintain the doubling of the quantum volume each year for a fair bit to come. Correct? Not everything will pan out, but there's enough different companies, enough different universities, enough different institutes working on many different parts of the problem that we are fairly confident that several of these things will start to add up.
Thank you.
Time for another quick question.
I'm Osama from TU Dresden, and I would like to ask a little bit about the security domain. Quantum computers may change the security domain, as an attacker may explore the whole state space in less time, for instance, a brute force attack. So could you please say a few words how you foresee the application of quantum computers in the security domain, please?
Yep. Yes, I mean, I think there are two parts of the question. So correct me. So to do quantum decryption, you need a very powerful quantum computer. Yeah. So we are a few steps away from getting to such a powerful quantum computer. However, as you rightfully point out, correct, it is absolutely time to start to think about quantum resistant encryption standards. Yeah? Because people are encrypting data today that needs to be kept for 10, 20, 30 years, correct, in the medical areas, in the financial areas. So you absolutely want people to start to use quantum resistant techniques, to do encoding and encryption of that data. So in IBM, we also have a very sizable research effort and actually a very sizable consulting effort where we are working on quantum safe encryption algorithms. We are working very closely with the NIST and the US government to make some of these official standards. And we are consulting companies on how to encrypt their data so that it will be quantum resistant at the right point in time. Yeah, so very good question, and certainly something that is the right time to start paying attention to.